Today we're going to take a look at trigonometric substitution, which is different than trigonometric integration, which we did last time. We did trig integrals last time. So last time when we were working in 8.3, we had functions that were given to us and they looked like trig functions, right? They had sines and cosines in them and so forth, and they had powers of these things, and we had some strategies or guidelines about how to go through and figure out what kind of a substitution a lot of times to make or what to pull out in order to make the things we've done before work for us, okay? We're going to be doing something a little different today. And in fact, the things that we look at on this front sheet of paper, if you've printed this out, don't look anything like trig, but they will shortly. Okay, so the method that we're going to be using today is going to involve radicals. The radicals will all have the form of a square root of two pieces that are either added or subtracted together. So we have a squared minus u squared, a squared plus u squared, and then we flip them and we do u squared minus a squared, which seems like it should be the same, but it actually has some nuances that make it different, okay? And the objective will be to eliminate these radicals by using Pythagorean identities. Okay, Pythagorean identities, like the trig ones. So real quick, let's jot those down so that we have them in the notes and so that you have them to be able to flip back to quickly. So the first one I'll do for you. It's sine squared plus cosine squared equals 1. That's the one everybody remembers. What's another one of them? We encountered them last time. Tangent squared plus 1 is equal to secant squared. Do you remember the third one? Cosecant squared plus 1. Cotangent's the last one. It's equal to cotangent squared. Okay, we're going to be pushing into these. And you might be looking at that and saying, Dr. Hans, I don't see any direct correlation between what you just wrote down and any of those radicals above. That's okay. You will shortly. So what I'd like to do in the first bit, the first three, thinking it was 3. The first 3 problems is to show you why we're doing what we're doing and where they come from, like where these pieces come from. Because I really feel like that a lot of times in mathematics, especially if math is not your favorite thing ever, you feel like somebody just pulled something out of the sky and they put it on paper and they said, this works. And you don't really have a good reason of why it works. You agree? It happens a lot. It happens even with the little bitty ones, right? When they're adding and subtracting sort of like 2-digit numbers for the first time and they get it like, they do 7 plus 8 and they get 15 and they have to write the 5 down and they pull the 1 up to the next column. What the heck? Like, why did that happen? Well, there's a reason for it, obviously, but we don't do a great job all the way through with explaining why things work. So I want to take a minute for the next 3 problems to explain why this works. Not because I'm going to ask you to prove it later, but because I want you to have some sort of sense of this makes sense, and it didn't just come out of nowhere. And it's actually hinging upon something that you already know. Okay? Is that fair? All right, so here's our first one. We're going to use these 3 identities, not identities, but these 3 different integral, that's not the word I want either. Radicals is what I want. These 3 different radicals that I'm going to show you it for, okay? So the first one is actually telling us, and this is important, like you need to know the actual substitution. When you see a radical of a squared minus u squared, the substitution you are going to make is going to be to replace the u with a sine theta. That's the substitution. So in terms of what do I have to actually be able to do with this information, you have to know this piece of information and be able to use it. But I want to show you why this substitution is the right one. Like, why does it work? And I'm going to show it to you in 2 different ways. One way is algebraic, so that's nice. And the other way is geometric, and it's also nice. So hopefully by showing you both options, one of them will be like, oh yeah, I get it. It makes sense, or at least it's justifiable for why it would work. Okay? I'm going to do the algebraic one first. And in order to show you the algebraic one, what I'm going to do is I'm going to actually put it in and show you what happens. Okay? That's what we're going to do. So we're going to put in, for you, a sine theta. So this is minus, and then I have a sine of theta squared. This is the substitution, kind of like a u substitution, but it's a trig substitution. And we're going to simplify this. So if I simplify this, I now have a squared minus a squared sine squared of theta. They both have an a squared in them, right? Okay, cool. So I can pull the a squared out, factor it, and I would have 1 minus the sine squared of theta. I can separate this as the square root of a squared and the square root of 1 minus sine theta, sine squared theta. I'm able to do that because the a squared is multiplied by that. That's a property of radicals from an algebra course. We do it in college algebra here. It's probably algebra 2. It's far enough along that it would be an algebra 2 course like in high school. But the square root of a squared is a. And then what's the square root of 1 minus sine squared? I shouldn't say it that way. How about just what's 1 minus sine squared first? That's cosine squared. And what's the square root of cosine squared? That's cosine. So why does it matter? Well, it matters because I'm able to simplify the radical into something that completely eliminates radicals. I turned something in radical form into something with trig form, which puts it back into section 8.3, and we can work with trig functions this way. Sometimes even easier without the 8.3 stuff. Adrian?
Could you have also used cosine instead of sine at the beginning?
We're going to see a substitution for something else later.
Okay.
Yeah. It doesn't work as nicely as it would to make the substitution differently. These substitutions are done in particular because they have very few restrictions. There is a restriction I need to know and need to make mention of for you, is that this only works, and I'm mentioning it only for the sake of like saying that it's not something we're going to have to worry about for the most part. Most of our integrations are not definite integrations, but if we had a definite integral, it would matter that we had this information. This will only work for negative pi over 2 to pi over 2 for my values for theta. Okay, so what we just did is what's called analytic justification. We're showing analytically how making that substitution makes it friendlier. Maybe not necessarily how we're going to use it. In fact, it's definitely not showing you how you're going to use it, but it's showing you how you can replace a radical with something in trig form, right? If I make this substitution for you, it will turn into something that I don't have any more radicals for. Let me show you what it looks like, though, in geometric form. We're going to see how well I do at drawing a right triangle. Not too bad. Okay, so we're going to do a right triangle. And I want to take this substitution quantity that I'm being told, and I'd like to put it into the triangle in a way that makes the angles and the sides of the triangle all sort of correspond, right? Think geometry. Think SOHCAHTOA. Y'all with me? So if I were to rewrite this right here, I would write this, the sine of theta is equal to what? U over A, right? I just divide the A to the other side, I can solve for sine. In my triangle, if I put this angle theta, in right here, what's the relationship between the sides of the triangle and the sine function? Opposite over hypotenuse. Okay, so if you're trying to remember how this works in terms of an acronym, this is what I had mentioned. SOHCAHTOA, we're working with sine. Sine is opposite over hypotenuse. So with U and A, the opposite would be U, and the hypotenuse would then be A. Okay, pretty good? All right, what's the third side, then, in terms of U's and A's?
A squared minus U squared.
It is A squared minus U squared. Why, Tanner?
The Pythagorean theorem.
It's the Pythagorean theorem, right? So we mentioned over here that we were going to be working with Pythagorean identities. If I'm using the Pythagorean theorem here, that sort of makes sense. I've got a right triangle, right? The two sides squared have to add up to the square root of the hypotenuse being squared, right? Like, I didn't say that quite right, but I think you know what I mean, right? A squared plus B squared equals C squared. So this third side down here would have to equal the square root of A squared minus U squared. Do you see that somewhere on the screen? That's the substitution we're trying to eliminate, right? Like the piece that we're trying to eliminate by substitution. Now, think about it with me for a moment. If I wanted to change what I'm working with, because right now, what will happen when I work with these is that the U and the square root of something with U in it are going to both be present, and it's going to make it kind of ugly and messy. You'll see in a minute why I'm talking about like that. But what we're trying to do is we're trying to eliminate having two variables in it. So in my triangle, there's two pieces of my triangle, two sides or hypotenuse. There's two of them, of the three, that have variables. The variable is U. Okay, A is a constant, so the variable is U. So the side lengths, namely like the opposite and the adjacent, those are the pieces where I have u's, right? So if I were to want to utilize the fact that I now have this square root that I've been working with and the side that does not have a variable, what is the relationship between those two orange pieces? That is, what's the trig relationship?
Oh, cosine.
It's cosine. I've got the adjacent side on the bottom, and I have the hypotenuse along over here, right? So the hypotenuse. So I could rewrite this as the cosine of theta is equal to the adjacent, which is the square root of a squared minus u squared, over the a squared. Over a, sorry, I don't know why I said a squared. Over a. This is the adjacent over the hypotenuse. And if I were to multiply the a to the other side, like this, look what happens at the bottom. I get the same thing that I did when I did the analytical way, right? I got a cosine theta. So if the u is equal to the a sine of theta, then that square root that I've been trying to eliminate will in fact equal a cosine theta, either from an analytical perspective or from a geometric perspective. Okay? If that feels a little bit uncomfortable, it's okay. We're going to do 2 more of them and it will get more comfortable because the process repeats itself quite similarly. So let's try the second one. Now I have addition in between, right? It tells me what the u substitution should be. It's a tangent of theta. We're going to do it analytically and then geometrically. Okay, so same song, second verse, right? All right. So we're going to do a replacement. A is our constant. Our variable is u, which will be replaced by a tangent of theta, and all of that's squared. If I simplify the component being squared, I can write this as a squared tangent squared of theta. Then what? Take the a squared out of those 2 pieces, which would leave me with 1 plus tangent squared. Then what?
That's secant squared.
Okay, so the square root of a squared is a, like that. And then the tangents, the 1 plus tangent squared is secant squared. And what is the square root of secant squared? It is secant of theta. The condition on the end of this one is much like the condition before. This works for negative pi over 2 to pi over 2. This has to do with both domain values, and it has to do with making sure things are 1-to-1. We've seen this happen before when we did inverse functions, so that's what this is kind of falling back into and why it's happening. So let's do a triangle and do the same thing. Whoops. There we go. So here's my theta in my triangle. How would I rewrite this to say tangent theta? It's tangent theta equals what? In a second. First with the, actually, I drew it with the yellow, so it's kind of hard to see right here. How would I rewrite this part first to get the tangent? Yeah, u over a. And then what were you telling me, Connor?
Opposite over adjacent.
Opposite over adjacent. So the opposite is my vertical piece. That one will be u. And my adjacent is the bottom piece. That one will be a. What's my third side? A squared plus u squared, or you could write it as u squared plus a squared, doesn't matter, right? And it's the square root. So I'm utilizing the Pythagorean theorem again. But then what I want is I want a relationship between the 2 sides here and here, right? The ones that don't involve the variable u. So what is the relationship between a and the square root of a squared plus u squared? Typically, what would we say? Cosine. It looks like cosine, right? So this is the cosine of theta. It equals the adjacent, which is a, over the hypotenuse, which is the square root of a squared plus u squared. Now, you might look at that and say, okay, well, that doesn't look quite like what I was looking for, and I'm supposed to be doing something with secant. So bear with me just like 2 more steps, and you'll see where the secant comes from. We're going to, for lack of better terms, cross multiply. You could also do reciprocals. There's several things you could do. I'm going to choose to write this one, which out like this, a squared plus u squared, and then it's cosine of theta equals a. And then to get the square root part alone, which is my goal, I would divide by the cosine of theta. So I have the square root of a squared plus u squared. It's a over cosine of theta. This, or a problem similar to this, shows up on your gateway, and some of you keep freaking out and don't know what to do about it, right? The trig identities or the trig functions in the denominator, you do not have a direct way to do that. You need to use the reciprocal function. So what's the reciprocal of cosine? Secant. So this is actually the same thing as having a squared plus u squared on the left, and then a secant theta on the right. And that's exactly where we got to over here too, right? A secant theta, a secant theta. Okay, we have one more to sort of justify why it's working for us. And it may sort of feel like, well, it's just subtraction like the first one, but there are some nuances to it because the subtraction is happening underneath a radical. So there are some nuances to this. So it says for trigonometric substitution, we're going to let the u squared minus a squared underneath our radical be equal to, or we're going to let the u be equal to a secant theta. Okay, so that's the substitution we're going to make to start with. So I have a secant of theta squared minus a squared. So this is a squared secant squared theta minus a squared. And then what do you see? Just like before, what do we do?
A squared times secant squared plus minus 1.
Yep, so we're going to factor out the a squared. Square root of a squared is a. We're going to actually come back to that in just a second and talk a little bit more. And what is the secant squared of theta minus 1?
Tangent squared.
That is tangent squared of theta. And then we are going to take, we're going to take the antiderivative, or take the square root and get tangent of theta. Because of the way this one pulls out with our radical, the other ones didn't have this happen, but this one does. So there's a nuance to this one. We actually get a plus or a minus on the a in the front. And you might be thinking, well, why don't we have that happen on the other two? And it has to do with the way that we are making our substitution. I don't really want to go into that too much. I just want you to recognize at this point we have two options. It's going to be either a positive a or a negative a tangent theta. And it will be clear which one you use when you need to use it. So don't worry too much about that right now. Just recognize that this one has two options. Okay, there's two options for it. And we have some situation pieces down here as well. So on this one, our angle actually goes between 0 and pi over 2. And then it pauses, if you will. And then it goes from pi over 2 to pi. Now, you might be thinking, well, why did I need to pause and stop at the pi over 2? Any thoughts as to why that might be happening on this graph?
Asymptote.
There's an asymptote, right? The tangent graph itself, down here, which is where we're ending up, has an asymptote at pi over 2. That didn't happen on the previous two. On the previous two, we didn't have asymptotes happening on those in-between spaces that caused problems, okay? So we do have this restricted in this way on this one for it to be causing a little bit of an awareness. Again, it's not a really huge, hairy deal. Just I'm putting it in because it's there. We don't really have to do much with it, okay? Let's do the graphical for this one, and then we're going to actually see how these are used because that's a little bit more directly applicable to what you're going to be doing, of course. So if I were to take this, like I did the last ones, and I were to rewrite this as secant of theta equals, what would it be? U over A. You bet. U over A. And we're going to draw our triangle so that we have those pieces there. Okay, so here's my angle theta. So secant doesn't directly go in from SOHCAHTOA. What is secant in terms of my triangle?
100%.
It's 1 over cosine. And cosine is adjacent over hypotenuse, so what's secant? Hypotenuse over adjacent. Okay, so it's the reciprocal of the adjacent over hypotenuse. So I'm going to have adjacent as my denominator now, so that's going to be my A, and my hypotenuse is going to be my U. So it's hypotenuse U over adjacent A. So then what's my third side?
Square
square root of u squared minus a squared, one more application of the Pythagorean identity, and that's exactly, or not identity, but the Pythagorean theorem, and that's exactly the part that I started with my radical, right? Okay, very good. So again, if I'm trying to get then a relationship that is sort of is going between my two components that don't have my variable u in them, right? They don't both have variables of u in them. I need my radical piece in there, and I need the constant piece in there. What trig identity relates those two pieces together? Tangent of theta. So the tangent of theta equals the opposite, which is the square root of u squared minus a squared, over the adjacent, which is a. And if I simplify, this is a tangent of theta, and it's equal to the square root of u squared minus a squared. Now, why is it a plus or a minus? Like, why does that show up? It has to do with how we drew our triangle. This triangle is drawn, sort of, if you can imagine sort of setting this inside of a coordinate grid. We drew all of our triangles inside of quadrant 1, correct? But this triangle, according to the way that this is described down here, could have been drawn in quadrant 2. And if it were drawn in quadrant 2, and this picture were flipped over that axis, the a value would be negative, wouldn't it? Can you picture it? If I took this picture and I had drawn it over here like this would be a negative value. And the reason that doesn't happen over here on these other two is because which two quadrants is this being drawn in? 1 and it would be 4. If I'm going down to negative pi over 2, right, I'd be drawing this in quadrant 4. And if this length right here that I've identified as a is in quadrant 4, my triangle just gets flipped upside down, but the a value is still positive, right? Can you picture that? If this picture had been drawn in quadrant 4, it's the same for the other picture. So if I'd drawn this in quadrant 1, I did it like this. If I drew it in quadrant 4, I'd be down here. And in either case, this value right here that I'm calling a is a positive value. And that happens on both of the first two. That's the reason, sort of from a graphical perspective, of why we're not getting the plus or minus. But over here, when I draw it as a value here, it would be there or here. And over here, it's positive, but over here, it's negative. Are you with me? Okay, that's why that's happening from a graphical perspective. Okay. But we should definitely see one of these in place so you can see how they work. They're actually very friendly. It won't involve any of the graphical pieces quite like what I've drawn, but we are going to draw some triangles in this section. All right, so we're going to take a look at an integral that has this square root in it. And as we take a look at this square root, the only method that we would have had to use, well, would have had two methods to use before this that we could try. U substitution, which might seem like it might work because I've got, a radical of x squared underneath, and the derivative of x squared would be x. That'd be fine if the x were being multiplied on the outside by the square root, but it's being divided. That's why I can't use U substitution here. I mean, it's not going to work. If you tried to use integration by parts with a radical, that would be terrible, wouldn't it? Because any derivative or antiderivative is going to have another radical with other like fractional coefficients in front of it. The other piece, which is the 1 over x piece, would have to then involve something with a natural log. Like, you're going to get nowhere fast, right? Like, really, it's not going to work, but you can kind of intuitively feel like it probably wouldn't. Like, there's a lot, it just gets messier no matter what I try and do. However, this actually does match one of these pieces that we saw over here. So which of these does it match? The first one. It matches the first one. And whoops, that was supposed to be a highlighter. It matches the first one. And that means that the substitution we're going to be using is that my u is going to equal a sine of theta. Okay? So this is exactly what we're going to be utilizing. We identify which of the three cases we're in, and we choose the appropriate u substitution for that case. So the u substitution for this case is a sine theta. Everybody good so far? Okay. So if I go over to this one, my u substitution is going to be, and it's not really u here, it's x because the x is my variable. So my x substitution is going to be equal to, what did I just say? Sine theta. A sine theta. Okay. So it's supposed to be this, but I need to figure out what the a is. It was a u that I wanted. The x was what I wanted to in place of the theta. I'm so sorry. Here's my x that I wanted to do. Okay. So if I do let me just write down where it started. It's u equals a sine theta. We need to figure out what the u and what the a and what the theta are based on the formula that we're given. So if we take a look at, not formula, but the antiderivative that we're asked to find. This piece and this piece. So this piece right here is matching up with the a, right? So if 16 is supposed to be a squared, what's a? A is 4. Okay, so I'm going to come back down here. I'm going to rewrite this as a 4. It'll be 4. And then the x is actually going to be what? Well, it's the u, right? So in place of u, I'm going to write x. So there's my x over here. And then I have my sine theta. Now I can get them in the right place if I take them step by step. Okay, so that's a valuable piece of information. The second valuable piece of information from this slide right here was where we ended up. In particular, we did a lot of work to get that radical to be replaced by something that wasn't in radical form but in trig form, correct? And what we ended up with was a cosine theta. So over here, the square root of 16 minus x squared is going to get replaced by a cosine theta. But what is a? Y'all know? 4. It is going to be 4 cosine theta. So when I replace the numerator of this function, the radical part, it will be replaced with 4 cosine theta. Okay, I am making a change of variable though, correct? I'm going to be turning x's into thetas. Can you see that? What that means is that dx on the end, it can't stay there either. So the last thing that I have to do, just like I would have to do in a u substitution, is I need to do the du, or in this case dx part. What is the derivative of 4 sine theta? Don't overthink this. Y'all know it. 4 cosine theta. Thank you. It happens to end up being the same thing that's over here with my dx. Okay? These 3 pieces of information, that is the dx, the x, and this one right here, where it's the 4 cosine theta, those are the 3 pieces of information that I need to use to substitute in. This is the trigonometric substitution. So I'm going to replace them in the original function. That's not what I meant to do. Let's try that again. Try it one more time. So the piece that's on top, this piece, will become what? 4 cosine of theta. The piece on bottom, here, x, will become what?
4 sine theta.
4 sine theta. And the piece at the end, dx, will become what? 4 cosine theta, and I should have put a d theta here. That's me being sloppy, so please include that. 4 cosine theta d theta. The problem that started out looking like radicals now looks like trig functions, correct? So either it's going to have something that's going to solve very nicely, which we'll see some of those, or it's going to have something that pushes us back into 8.3, where maybe we're going to have powers of sines or cosines or tangents or cotangents or something like that we're going to have to work with. So we need to clean this up from the perspective of trig now, okay? So we have lots of 4s here. Let's see. There's these 2 4s cancel, right? Give me a couple, or any of the 2. If you don't want to do those, cancel those 2. I don't care. But there's a 4 left over. I have 1 4 here. And then I have a cosine and a cosine. That's cosine squared. And I have this over the sine of theta. Okay, is that good so far? Okay, so if at this point you have powers, which you do, that means we're pushed back into 8.3. Okay? 8.3 talked about what to happen when we have powers. There was one of our properties that says that if the power is even on the cosine, then or on sine either way, we have I called it a power reducing formula. Do you remember that? Showed up sort of in the middle there. It talked about replacing it with, and it actually corresponds to a half angle identity as well. It takes the sine squared or the cosine squared and it turns it into cosines. So that's the step we're on at this point. So from 8.3, we're going to make the next substitution. We're going to use an identity. The identity, we still have the sine theta on bottom, is going to be replacing the first part with, I don't have it written down directly. Oh, you know what? It's easier than that. I think I'm thinking of a different one I'm doing later. there's an easier way to replace the cosine squared in something that's going to be helpful here. We can actually use a Pythagorean identity to replace this. What is the cosine squared if I turn it into sines? Because I've got a sine on denominator. Yeah, it's 1 minus sine squared. Sorry. Forgot that this one was even easier than that. The reason that this is very nice is because I now have sines on top and sines on bottom. And I can actually separate this because the addition is on the top, or the subtraction in this case is on the top, and have a single value on the bottom. So I can separate this out to be written as 1 over sine of theta minus sine squared over sine of theta d theta. All right, so let's clean this up one step more. What is 1 over sine of theta? Cosecant. Very good. Remember that for your antiderivatives. Some of you are still working on that. What is sine squared over sine? That's just sine. Okay, everybody good? At this point, whether you have it memorized at this point or not, I hope you do, we're looking at an antiderivative of two different individual pieces that are what we would call simple rules. They're direct rules that we have, right? Nothing fancy. What is the antiderivative of cosecant? Make sure I get my sign right. It's negative natural log. Cosecant of theta, and it's plus cotangent of theta. That's the cosecant part. What is the antiderivative of sine? Negative cosine, and there's already a negative here too, so it's going to end up giving me a cancellation with that negative, so this will be positive cosine of theta. I know I need a plus c, but let me close my parenthesis first and make this a little smaller to get it, since I'm running out of space. Okay, everybody good? I need to distribute the 4, but beyond that, I can't leave it this way. Why not? I started with x, and these have thetas in them, right? This is yes. Every time we need a u substitution, that's what we said at the end too. If it's still got u's in it, we got to bump them back into x's or whatever variable we started with. We started with x's. I need to replace these thetas with x's. And it may not be directly obvious to you how you can do that. We do have a relationship written down, right? That the u and the, not that one, sorry, this one's the one, that the x and the 4 sine of theta have this relationship. But going to that place is not going to be real pretty. So that's not what we're going to do. What we're going to do is we're going to go to a triangle. Okay? Just like we did 3 times before. We're going to create a triangle. And that's part of why I wanted to create the triangles and to show you why it worked, is because it's going to lend itself very well to what we need to do at the end of these problems anyway. So let me go ahead and I'll distribute the 4 through just so that we've taken care of that. We have negative 4 natural log of the cosecant of theta plus the cotangent of theta plus 4 cosine of theta plus c. Okay, so we're going to create a triangle. Do I have space in another one? I do. Let me actually, you know what? Let's just create a triangle over here and then I'll move it. So we're going to have a triangle. The triangle is going to have theta in it. And the relationship that we had written down was x equals 4 sine theta. So we're going to take this equation and we're going to solve it for sine. So the sine of theta is equal to x over 4. Where in my triangle does x go and where does 4 go? Yes, 4 is the hypotenuse, x is opposite. What's the part on the bottom going to be?
Square root of 4 squared minus x.
Okay, so square root of 4 squared, which is 16 minus x squared, like this. Okay, everybody good? Okay, now I'm going to move the part that I told you I was going to move because now we're ready to use it. Oops. Okay, so then using this triangle, we can figure out from the triangle how to get cosecant of theta, cotangent of theta, and cosine of theta, right? SOHCAHTOA. Let's start with cosecant. What would cosecant be for this triangle?
Hypotenuse over opposite.
Hypotenuse over opposite. It's the nice one, actually, of all of them. What is the hypotenuse over the opposite going to be in this triangle? 4 over x. Okay, hypotenuse over opposite, or the reciprocal of sine. So you could also think about that one pretty nicely just from the sine equation that we have written over here. It's x over 4, so now it's 4 over x. Cotangent, though, we really do need to see the picture to sort of think about this and get all the pieces in the right places. So what is the cotangent in this triangle going to be?
Adjacent over opposite.
Yeah, so tangent is opposite over adjacent. So cotangent is adjacent over opposite. So adjacent is that radical piece, square root of 16 minus x squared, underneath my square, yeah, there we go. And then over opposite, so that's 4 over x plus. And then how about cosine of theta? That's adjacent over hypotenuse. So the adjacent is the square root of 16 minus x squared over the hypotenuse, which is x, and plus c. Okay, truth be told, there's really not a lot of cleanup you could do. I mean, we can merge a couple of tiny things together. Like, we could make it a single fraction inside of our absolute values if you wish. That's not really very helpful. Yeah. Did I mess something up? It was 4. Thank you. Got it from the wrong spot. So that piece can be simplified, right? We could go ahead and cancel those pieces out. If you want, you can merge those two together as a single fraction. I don't really care whether they're merged or not, so I'm just going to leave them the way that they are. So this is 4 over x plus the square root of 16 minus x squared over x. And then we would have plus the square root of 16 minus x squared plus c. Okay, is that right? Okay, we're going to do another one. First, have to figure out which of the 3 cases we're in. 1, 2, or 3. Which one are we in? 3. No, I don't think so. I think it's 2. 2 is the one with addition, isn't it?
Yeah.
2 is addition. So it's number 2. Yeah, it's 2. So 2 is the only one with addition. So we're in case number 2. So the appropriate u substitution is that u is equal to a tangent theta. So this is the one we're going to be working with. U is equal to a tangent of theta. Now, in our picture, I guess I could also write this one down. Where's the other piece of it? At the end, the radical form itself is going to equal to a secant theta. We're going to need that. Let me write that down too. So the square root of u squared plus a squared equals a, was it secant theta? I think that's what I said. Okay, what are a and u? Well, this piece and this piece, right? So what is a? What is u? A is 3. So a is the constant piece. So that's the 3 from here. So in the place of the a's, I'm going to write in 3's. And the u is actually equal to x here, right? That's not right, sorry, 2x here. So this piece right here, which is u, is 4x squared. And then if I were to equal, how about x over 2? No, it was 2x. I wrote right. I'm going to get my over 2 in a second. So my u squared is 4x squared, which means my u is actually 2x.
Why do you have 2x there?
Because that's what u is. The piece that's being squared, that's the variable piece, is not just x, it's 2x, because I've got a 4 in front of it. Is that okay?
Why do you have 2x equals 3?
I'm not done. This will say tangent of theta. Yeah, I wasn't finished. So the a was replaced by the 3, the u is replaced by 2x, and then I've got my tangent of theta still in there. What I do want to do, though, is to recognize that I don't have 2x out here in front, right here, right? I just have plain old x. So I am going to solve this, and so my x is actually going to equal 3/2 tangent of theta here. Okay, because I have the x in there, and I also have a dx that I need to find for at the end. So what is the derivative of x? I'll give you the 3/2. Secant squared. Okay, so dx. So these three pieces are the ones that I need. I need this dx, I need this x, and I need this square root piece. Those are the three pieces I need for a trig substitution. U substitutions only need two pieces. They are these pieces over here on the left. But with a trig substitution, the whole goal is to get rid of the radicals. So I need the radical piece as a third piece for the substitution. So we're going to take all of this information. We're going to shrink it first over here a little. And we're going to make our substitutions. So this is an integral. 1's fine. X is 3/2 tangent theta. The square root piece is 3 secant theta. And then the dx piece is 3/2 secant squared theta. Did I get all those pieces in there right? Yeah, I think so. It's okay? Got all of our pieces in there. Let's reduce some things. What pieces do you see that could cancel? One of the secants will cancel. So this secant squared will be a secant, and this secant will cancel. What else? The 3/2 will cancel. That's friendly. I think that's it. I still have a 3 in the denominator, so I'm going to pull out a 1/3 in the front. And I now have secant theta over tangent theta, d theta. Now, I didn't show you an example of one last time, so that's why this is included this way this time. This does not fit in with any of the things inside of Section 8.3 about what to do directly. It's in the default that happened at the very bottom that I said, when all else fails, we convert to sines and cosines. This is an example of that. This one doesn't fit into any of the earlier categories. We're going to turn these into sines and cosines. So we're going to separate them. I'm going to actually write them sort of separately. So let me try to write this as secant of theta. What's that?
1/3.
No, because it's supposed to be 1/3. Thank you. Secant of theta, and I'm going to write this as 1 over tangent of theta, just so we can see the pieces. I don't know. I like to see it that way. That's how I'm going to do it. All right, secant is going to be what in terms of sines and cosines? 1 over cosine. How about 1 over tangent, which would also be known as cotangent? Cosine over sine. What's happening? Cancelization. That's a good word. Okay, cool. Cancelization happens. So we canceled the cosines. So we're left with a 1/3. And we have 1 over sine, which is otherwise known as cosecant of theta d theta. Now, you may not like cosecant, but it does have a closed form that we're aware of, correct? Okay. We're going to need to find that in a moment. Actually, you know what? Let me just do that first. Let's go ahead and do the antiderivative. What's the antiderivative of cosecant of theta?
1/1 cosecant, or also that cosecant.
I didn't even write it right. Okay, it's negative. So negative went in front of my 1/3. It's natural log, and it's the cosecant of theta and cotangent of theta added, plus my c at the end. So this is the answer. It's just not finished because it's still in terms of theta, right? So when we get to the point where we've done our antiderivative, we still need to turn it back into u's and x's or whatever our variable was to start with. This one had x's, so we're going to draw a triangle to help us to do that. And the relationship that we started with over here was that, I don't care which version of it you use, but one of these versions of it right here, right? One of these two versions is fine. I'll just use x equals 3/2 tangent. I'll just use 2x. I'll use 2x equals 3 tangent theta. I want to rewrite that with tangent theta in mind. So tangent of theta is actually 2x over 3. Okay, so in terms of my triangle, and theta being right here, what goes where?
2x is the vertical.
2x is the opposite or the vertical piece. 3 is the base or the horizontal piece or the adjacent, right? What about my third side over here? It'll be a 9 plus 4x squared, or you can do 4x squared plus 9 if you wish. Right? That's exactly the square root piece that I have right here, correct? So if you're finding the third side, it should be the missing third side. That will happen all the time. If it doesn't, you've got an error somewhere. It may be just in creating your triangle, but there is an error that's happening. All right, within this triangle now, I have my negative 1/3 natural log. What is the cosecant value? It's 1 over sine. Sine would be opposite of hypotenuse. So cosecant would be hypotenuse over opposite. So hypotenuse is the 9 plus 4x squared over the opposite, which is 2x. Okay, what about cotangent? Right, so cotangent is the reciprocal of tangent. Tangent is opposite over adjacent, so cotangent is adjacent over opposite. Adjacent here is 3, and opposite is 2x. And then we have our plus c at the end. Again, the only thing that we really could do here at all is make this one single fraction inside the absolute values. Choose to do it, choose to not do it. It doesn't really matter to me, but this is as simplified as it really gets. Okay, there's one more thing in this section, but you're going to like this piece. Not that I'm saying you didn't like the other pieces, because I know beyond a shadow of a doubt that you did. But this is going to feel very simple by comparison. How's that? Is that good? That's good. That's helpful. Okay. So there are 3 special integration formulas. Now, here's why it's simple. No. Slow down, Levi. I promise you, Adrian, slow down. Here's why it's simple. Is that it's like when you're given something that you can just use without having to do the antiderivative for. So you identify that it looks like something on the left, and you don't have to do any antiderivatives. You just have to plug it in and evaluate it into what's on the right. That's why it's simple. Nobody's asking you to memorize these. But these kind of should look a little bit similar to some of the things we've just been seeing, right? In fact, all 3 of the ones on the left are exactly 1, 2, and 3, but in a different order, just because they used the order they gave you of what we already did, right? These are the 3 that we already did. And we did all the work to figure out how they work and how to do them, and now here's something that just says, okay, but the general form that always ends up at the end is what's on the right. So if you have problems that ask you to do them with special integration formulas, they're asking you to do them with this method and not to go through all of the creating the triangles and doing the integration that we've done on the previous 2 problems. So jot those down. And we're about to go off script because I think I'd like to change my last problem. So once we get those written down, we're going to make one small change to our last problem. Okay, are you ready? Oh, couple, you're still writing, sorry. Okay, if you wrote this slide down in long form, because those of you who have it printed, it's already printed for you. If you just wrote this down, why don't you get out your phone and take a picture, because I fear that you might have missed a sign or a squared or something else that's going to cause you problems later. So I want you to just take a real quick picture of my slide just to make sure later on that you did not make a mistake writing something down, okay? Because if you do, that's going to cause problems, obviously, and there's a lot of pieces here. Okay, are you ready? This is the problem. We're going to change it, and I want it to just say a 4 here. If I change it to saying a 4 here, what is this problem? It's 3. It's the one we just did. I think it was called 2. Oh, I think probably messed my numbers up. Oh, it's the problem we just did, right? In the denominator. But it's that piece, correct? It's the square root of 4x squared plus 9 piece, but it's just all by itself. All right? So what I want to do, the reason I wanted to change it as I'm thinking about it and it's just starting, is that I want you to see how different it feels when you use those pieces with basically the same thing we had before, instead of doing it with the whole process that we did before. Okay, the pieces are pretty much the same. I realize they're not in the denominator and all that, but it doesn't matter. The process will still be the same, whether it's like this or whether it was like the way that it was written in 1b. Okay, so what this is saying is that I first need to decide which of these 1, 2, or 3 we're using, and I think that's where the 3 was that you went to. This is number 3, correct? It looks just like this. Now, technically, we could go through all of the process that we went through, which matches up to this one, and we could do it like that, right? And if I'm asking you to do it with trigonometric substitution, that is what I will expect to see. However, if I ask you to do it in any way, which way you want, then you can do it with special limits. Or they're not special limits, but special trig integrations. These pieces right here, okay? So we're going to do it from this perspective, which what it really means is I need to identify what is U and what is A. That's all I have to do. Are you with me? So in our formula, I'm going to just write it over here so that we can identify them easily. It said 9 plus 4x squared dx. Okay, so using this information, what is U? Actually, I'm going to write it over here. U is what?
3.
Nope. 2x. Okay, why?
U is always the variable.
U is always the variable piece. So what is A? A is 3. So over here on the right-hand side, I'm simply going to replace all the U's and the A's with the 2x's and the 3's. There is one caveat. The caveat is that I need to make sure that I do the derivative of U, which gives me an extra 2 dx. There's going to be a 2 that's going to show up because my variable is not just a variable, it's a variable with a coefficient. So this 2 right here will go at the front of this with my 1/2. So I will have a 2 from the du part, and then I'm going to have the 1/2, and then I'm going to continue. So U is 2x. The square root's the same square root. I have 2x squared, so that's 4x, and then the squared on the outside, plus my 9. Plus, I have a squared, so that's 9. Natural log of the absolute value of the u, which is 2x, plus the square root of the u squared plus a squared, which is 4x squared plus 9. That's an absolute value. Close my parenthesis, plus c. Okay, I'm just putting this over here. Okay, well, there we go. I didn't take an antiderivative, did I? Nope. All I did was figure out what is u and what is a. And because u is not just a variable, I had to do a du. So I have this 2 showing up at the beginning here. That part's a little bit unique on this particular one. If it didn't have the coefficient, it wouldn't be there. And the only thing that there is to do is to simplify what we have left, which is, in this case, just to multiply the 2 and the 1/2, which is not going to be anything, and to write this really without the parentheses. So I have 2x square root of 4x squared plus 9, or you could do 9 plus 4x squared, plus 9 natural log, the absolute value of 2x plus the square root of 4x squared plus 9 plus c. Okay, so here's your warning. Could I use these problems here and here? Okay. I could, right? At least I maybe could. They have some of those pieces involved in them, so they stand a chance when I look at anything that has those pieces in them of being able to be utilized. The two that I chose you couldn't because they're a little bit more complicated, right? They've got an over x, or in this case, the next one, this case had the square root in the denominator. So these two specifically could not be used with this. But if I have this particular problem, I could have directions that looked just like the problems I had on 1A and B, right? And I could do it by hand, and I could be asked to do it by hand, and that's a legitimate ask. Yes?
Where did the 2 come from at the beginning of the...
It came from the derivative right here of the 2x. Because u itself has, I'm doing kind of a substitution step without showing it, and the du would actually be involved in there, which would have a 2 in it. That's where that 2 is coming from. So if you have any variable component that has a coefficient, it shows up, okay? But what I want you to do is to use caution. If you see something in your work that asks you to do it with trigonometric substitution like we did on 1A and B, do it that way. Feel free to check it the other way if you wish. That's fine. But I'm going to ask you to do things with some trigonometric substitution, and I want you to have fair enough practice that you feel like I know how I'm going to be doing this. Not just going to default to those formulas because I can. They're able. They're there. Okay? All right, we'll pick back up next time. So next time, we will pick back up with 8.5 and 8.7. Okay, there's no quiz next time. That was pushed to the Thursday. And we'll be late. I will be late on Tuesday as well.